Welcome to the debate. Today, we're wrestling with a question that's really central to the integrity of geotechnical practice. It's rooted deeply in the MI303 course material on site characterization, and specifically how we manage uncertainty and variability. The question we're asking is this: does our persistent, almost obligatory reliance on traditional empirical index properties, specifically the rock quality designation, RQD, and the hardness field assessment, or R values, does this fundamentally compromise the scientific integrity and accuracy we need for modern rock engineering design? My position is that yes, it does. These established methods are often inherently subjective, prone to severe misapplication, and frankly, their continued use reflects a kind of professional inertia. We need to shift toward truly quantitative, scientifically rigorous measurements.
And I'll be arguing that we need to consider the necessary practicality of these tools. Now, I fully acknowledge the theoretical limitations and the philosophical critique, this idea from the material that we must sapere aude, dare to know and to challenge our assumptions. I get that. But these established index properties are, for now, essential. They provide the necessary, accessible initial quantification that we require to manage the inevitable uncertainties in complex real-world engineering projects, especially in situations where time, budget, and access restrict us to 1D borehole data and where we simply don't have prototypes to test our assumptions.
I see why you think that industry standards offer utility, particularly, speed and convenience. But let me give you a different perspective, one that's drawn from a necessary philosophical rigor. The source material is, it's unequivocal. It says, industry standards should not be sacrosanct and immune to changes. And yet, our current practice of core logging and using indices like RQD often reflects a very deep contradiction. My core objection here, it really stems from epistemology. Many parameters we assign numbers to in rock mechanics are not true quantities. They lack the mathematical properties of additivity and continuity. The act of assigning a number to a qualitative assessment, like a hammer strike or a visual guess at fracture spacing, it doesn't magically make it quantitative. We are actively cultivating two of Francis Bacon's great intellectual hazards here. The idols of the theater, which is this deep-seated, uncritical acceptance of methods just because they've been passed down. And then the idols of the cave, which manifests as the personal subjectivity introduced by, varying core logging manuals and an individual's judgment. This subjectivity, it poisons the very foundation of our geological model, and that renders any subsequent sophisticated numerical analyses built upon that shaky ground, philosophically meaningless. We have to demand true quantification, not just assigning numbers.
Yeah, but I'm coming at it from a different way. We have to anchor this discussion in the practical realities of geotechnical engineering. The material itself notes that rock engineering design is often like building a plane as you fly it. We almost never have the luxury of developing deep access to rock exposures before the design cycle demands these preliminary decisions. We're relying overwhelmingly on limited 1D borehole data. And while I accept your philosophical point that assigning a number to an assessment doesn't make it a ratio scale quantity, these index properties serve as an absolutely essential bridge. They offer the necessary initial quantification of a largely qualitative description. This allows us to manage what we define as uncertainty, the known unknowns, which we can and we must address using probability functions and statistical distributions. Now, yes, they are completely ineffective when you're confronted with radical uncertainty, the unknown unknowns. But let's be fair, no existing statistical method can address that challenge. Index properties, they have historically formed the very bedrock of successful classification systems like RMR and the Q system. They provide a practical, relative measure of rock quality that allows us to move forward during those critical early stages. To just discard them is to halt initial design progress entirely.
Okay, let's delve into that bridge you're championing, specifically the hardness field assessment R values, which are detailed by the ISRM. This scale is explicitly an ordinal scale of measurement. It denotes order. R3 is harder than R2. But critically, the difference between R1 and R2 is not mathematically equivalent to the difference between R3 and R4. So I'm not convinced by that line of reasoning that it's a functional bridge, because the real danger The real danger lies in how practitioners routinely abuse this tool. The source clearly and strongly warns against common misapplications. It says engineers must not use decimal figures, like claiming something is R2.5, nor can they calculate the mean and standard deviation of a series of R values. The material actually labels this practice as an example of a nonsense calculation.
But the material itself clarifies that the issue is a lack of conceptual clarity, not that the tool is inherently useless.
It is useless when it's misused. When practitioners knowingly take this qualitative assessment and then treat it as if it were a quantitative measurement, they are manifesting what the course calls preferential attachment biases. They're just preferring old habits and simplified calculations over actual scientific validity. And, consider the tangible consequence of this nonsense calculation. If I calculate the mean R value for 20 points in a tunnel, I arrive at a single number, let's say 3.7. That numerical average provides a completely false sense of precision and homogeneity. It actively obscures the true geological variability and the possibility of localized weak zones, an R1 or an R2 that just got averaged out with stronger rock. This homogenization can lead directly to non-conservative and potentially safety-critical design choices because the model fundamentally underestimates the dispersion of the data, which is where risk truly resides.
That's an interesting point, though I would frame it differently. The scale itself serves a vital purpose as a rapid field-based reference point. It provides a quick classification that, yes, loosely and qualitatively correlates to strength ranges. R4, for instance, often indicates a UCS of 50 to 100 MPa. Its inherent simplicity makes it exceptionally useful for initial characterization and for quickly identifying significant variability or changes in rock type across a site. So the primary solution isn't to just discard the tool, it's to enforce rigorous training on the 4 classes of measurement: nominal, ordinal, integral, and ratio. If an engineer understands that R values only permit calculation of the mode and that they must not extrapolate decimals or calculate the mean, then the index remains entirely functional and practical. It provides a starting reference point when the detailed, costly, and time-consuming laboratory testing required for true ratio scale measurements is just unavailable in Phase 1. Aren't you asking for the perfect to be the enemy of the good here?
Fixing the training it only partially addresses the deep intrinsic flaws in tools like the Rock Quality Designation Index, or RQD. Let's attack the fundamental arbitrariness there. Deere's original decision to use a 10-centimeter threshold for scoring is, by definition, arbitrary. That 0.2 centimeter difference between a 9.9 centimeter piece scoring 0% and a 10.1 centimeter piece contributing fully to the RQD score, that's a mathematical discontinuity that directly biases the result. And more critically, RQD is often calculated over a core run length, typically 1.5 to 3 meters. As the material emphasizes, this run length is a drilling artifact, not a geological unit. We are conflating measurement convenience with geological reality. A highly fractured seam that should represent a localized weakness can be effectively diluted or, averaged out with a long stretch of competent rock, just because they happen to fall within the same core barrel run. This homogenization fundamentally misrepresents the rock mass structure, which is the most crucial input for a design.
I agree with your theoretical critique on the arbitrariness of the 10-centimeter cutoff and the dependency on the drilling technique, but RQD's historical success really speaks for itself. The RQD definition, while imperfect, it provided a means to quantify core logs, particularly for NX core sizes, back when no other easily applicable metric existed. It remains extremely useful as a relative measurement of good rock recovery. It signals significant differences in overall rock mass quality across a site. The limitations you cite, its direction dependency and the core run artifact, are really just reflections of the harsh reality of 1D sampling. So if an engineer is acutely mindful of these limitations and uses RQD strictly as a classification input,
Acknowledging that its measurement uncertainty far exceeds a 5% margin, it still offers necessary foundational data. To throw out RQD requires us to dismantle the entire scaffolding of widely used and, I would argue, demonstrably successful systems like RMR and the Q system. I mean, these are systems that many infrastructure projects still depend on globally. So how many successful projects built on the back of these classification systems would you be willing to discard for the sake of, what, philosophical purity?
I wouldn't discard the systems. I would demand they be calibrated using truly quantitative measurements, like detailed fracture frequency or joint persistence mapping, instead of these flawed proxies. The danger is precisely the averaging effect. If two different stretches of rock yield an RQD of 75%, but one achieved that score through a few large, highly persistent fractures, and the other achieved it through a high frequency of short, non-persistent fractures, those two rock masses will behave radically differently under load. RQD hides this essential variability. And this is exactly why we must prioritize discrete fracture network, or DFN, analysis based on ratio scale measurements of fracture length, orientation, and spacing over a highly aggregated nonlinear index score.
But you're advocating for a level of data resolution and input complexity that is often just impossible or prohibitively expensive in the initial stages of a major project. RQD gives us an immediate, rapid answer about overall quality. DFN models, while, yes, scientifically superior, they require significant computational power, time, and data input that often only become available much later in the design cycle. We need to characterize the rock mass when we're flying the plane. RQD allows that initial classification. It's the first filter.
Even when we agree on the initial data, whether it's flawed or robust, we immediately face another fundamental problem when moving from the characterization scale to the design scale, and that's the issue of scale effects. Our initial observations are at the core scale, in centimeters, and these must be extrapolated to the engineering scale, meters, tens of meters, for actual design implementation. So we're forced to rely primarily on empirical scale relationships, which are just rules of thumb derived from past experience instead of fully validated analytical scale functions. And this introduces massive, unquantifiable uncertainty simply by changing the size of the rock volume under consideration.
That's a compelling argument, but have you considered the context? The data collection process should be inherently driven by the anticipated failure mechanism and the problem size. The distinction between the behavior of intact rock, or Chile, and the behavior of the rock mass, DN, is absolutely critical here. Index properties apply primarily to the intact rock component, so the upscaling challenge is inherent to rock mechanics. It's not solely the fault of the indices we choose. Moreover, the material itself notes that new technologies, LiDAR, photogrammetry, drone mapping, they offer tangible opportunities to reduce uncertainty by acquiring high-quality 2D and 3D geometric data remotely. The solution isn't discarding the empirical foundation, but integrating it carefully with modern geometric data that helps bridge that scale gap.
I appreciate the optimism about new technology, but the issue of data hygiene and transfer during the design process introduces a subtle yet profound source of new uncertainty, entirely independent of the scale effect. Just consider the data processing pipeline for a moment. If the field engineer performing the mapping uses a cutoff or a censoring effect, let's say they only map fractures longer than 5 millimeters. But the numerical modeler who receives that data weeks later is entirely unaware of this hidden filter, they will process the data assuming they have a complete representative sample set.
But that's just a communication failure, not a data measurement failure.
It's both, because the reliance on index properties and qualitative judgment creates the very environment where hidden censoring can thrive. When that modeler calculates the factor of safety based on this artificially homogenized, filtered dataset, the result is systematically biased, typically toward a non-conservative model, because the apparent fracture frequency is lower than reality. The uncertainty hasn't merely been managed, it has been introduced or actively created, simply as data move through the design pipeline.
and all because of a lack of philosophical grounding regarding what the data truly represents. While LiDAR gives us fantastic surface geometry, it tells us nothing about the subsurface volumetric strength and continuity, which is the exact domain of core logging. We're just trading one uncertainty for another.
But the empirical tools, if they're used properly, they offer a way to check those advanced models. You're arguing that because we cannot perfectly quantify every single aspect of the rock mass behavior, we should reject the available tools that allow us to make initial effective decisions. That is fundamentally impractical. In fact, the practical utility of RQD is that it forces a degree of standardization at the logging stage, which is absolutely necessary when you're coordinating across multiple sites and teams. If we remove all these classification proxies, subjectivity will not disappear. It will simply shift to the judgment required for complex constitutional modeling, which is far less transparent than a simple RQD number. The goal should be interpretation and integration, acknowledging the index properties' limitations while recognizing their irreplaceable role in early-stage risk management and resource allocation.
So to summarize, the philosophical lens reveals a deep and persistent contradiction in how rock engineering handles fundamental data. We have to move beyond this reliance on methods whose continued use reflects professional inertia more than it reflects scientific validation. The fundamental need is to recognize and to respect the mathematical hierarchy of measurement. We must know which parameters are truly quantitative, those on the interval or ratio scale, like measured fracture persistence or tensile strength, versus those that are merely qualitative assessments on the nominal or ordinal scale, like R values. The long-term integrity of our geotechnical models depends on stopping the practice of assigning false precision and mathematical properties to qualitative data.
And my summary is that data collection methods must, above all, be practical, accessible, and timely, especially given the high degree of geological variability and uncertainty we confront when we have no prototype to guide us. While I do agree that the philosophical critique you raise sharpens our understanding of data limitations and cognitive biases, and we absolutely must improve statistical rigor, index properties like RQD and hardness assessment, when they're used with intellectual humility and an awareness of their classification function, provide essential foundational data points. They are required for initial characterization, for risk assessment, and for guiding resource allocation in the early stages of a project. They allow us to manage the known unknowns.
And so the challenge remains achieving that critical balance for engineers between the speed and convenience of established empirical methods and the philosophical, and I would say non-negotiable demand for true scientific rigor in these complex systems.
It is a vital tension and one that drives the field forward. And the rigorous challenge itself is the path toward advancing engineering knowledge. Thank you for the exchange.
Welcome to the debate. Today, we're wrestling with a question that's really central